So I want to talk today about Memcached. This is a paper from Facebook from 2013. Memcached is still widely used, and many websites or big internet websites have ideas or architectures very similar to it. The paper is an experience paper. So the goal of the paper is not so much to introduce new ideas or new concepts or new innovative ways of building systems, but it's more to report on actually practical experience in trying to build systems that, in this particular case, can support 1 billion requests per second or multiple billion requests per second. And so there are sort of 3 lessons that you can take away from this particular paper. One is they got very impressive performance out of building a system with off-the-shelf component. And so the system consists of standard open software packages like MySQL, Memcached, and they combine that together to actually build a system or scale that out to a system that can actually support 1 billion requests per second. As you will see, in this lecture, there's sort of continuously a tension between performance and consistency. And as you will see in this paper, the design is mostly driven by performance, but they want to provide some degree of consistency. And the sort of that is sort of added to make the system at least be usable for the applications that actually Facebook has. In fact, the consistency model is quite different from the consistency models that we've seen before. Most of the systems that we talked about so far actually provide either external consistency or linearizability, very, very strong forms of consistency. And in the case of Facebook, their applications don't really need linearizability. If a user is reading news articles and the news feed is a couple seconds behind, doesn't really matter. And so they have absolutely not the goal of providing sort of linearizability or strict consistency. So that's an important thing to keep in mind. Despite that, they're not shooting for strong consistency. There are some sort of cautionary tales in the paper that adding consistency measures is not easy if you sort of not have prepared for them from the start. But nevertheless, you really can't argue with the success of the system. It's clearly very successful and allows Facebook and websites that follow or internet companies that follow similar strategies to actually scale to a large number of users. So my plan for this lecture basically is first to talk about performance, because really the performance is the driving force behind this design, and then at the end talk more about consistency. Before jumping in though, let me know if there's any questions. Okay, so let me start with sort of a little bit of a broader introduction to performance. And basically sort of talk about like website evolution. Now, I'm sure many of you actually have built websites, and if you sort of start out and you don't have any users, that's pretty straightforward. You buy a machine or rent a machine on Amazon or anywhere else, and you just basically need 3 components. You need a web server, so let's say Apache. You need a sort of an application framework to build your website in. Maybe it's PHP, maybe it's Python. In the case of Facebook, I think they use PHP. And you need a database to actually store the data of your website. And so, for example, you might use whatever MySQL as Facebook is doing. And so clients connect to your website. run, the whatever application code, whatever application service the website provides, and store and retrieve data using the database. The database provides transactions. It has SQL, so it's easy to query over the data in different ways. And all the persistent state is stored in the database. So you just have to back up the database, and you basically have a good sort of fault tolerance plan. And that's sort of the and for any website that has a small number of users, this is completely sufficient, and the way many websites are built. However, when the number of users increases, you probably need to go to a little bit more sophisticated design. So this is sort of step one in the evolution. And in step two, you sort of try to address the first bottleneck that you will run into when you have a larger number of users. And typically the bottleneck that you will run into is basically the computation of the cycles being used by the application. So if you have thousands of users running at the website at the same time, or 10,000 or whatever number of users it is, and just the running the application code on a single CPU or a single computer gets to drives basically the CPU load up to 100%, and then you can't support more. And so fortunately this is actually straightforwardly solved because the database actually has all the persistent state. So the typical way you solve this is you keep the one machine with the database, and keep the machine on the database, and then just buy a bunch of different machines for the front ends. And I'm just going to talk about the front end as one thing, which is typically the website, Apache, plus some application code. And you just if you get more users, you'll buy more machines. They all connect to the database to get their data. And actually this design works out extremely well because basically the front ends are stateless. All the state again is in the database, and so adding a new server is pretty trivial. All the front ends actually will see the latest writes because all the data is actually stored in the database, so there are no consistency issues. In terms of fault tolerance is easy. If one of these machines fails, no problem at all. Maybe the other machines have to take over the load, or you have to bring on a new machine in line, but you don't actually have to do anything in terms of complicated data restoration or restoration because all the data is actually in the database. And so this is a good, typically this is the first thing that happens as a website scales. Now, of course, if your website scales further, and you need to support more than, say, for example, a simple MySQL setup can probably support 100,000 simple read transactions or simple read queries per second, probably thousands of write transactions. And so if the total number of requests from your users actually goes over that 100,000, then you need a different plan. And so then the next plan is typically sharding. And so far this is all pretty standard. And so what you do is actually you take the storage machine and you split it in multiple machines. So the front ends basically stay the same. We still have our any front end machines. And here we have our sharded database, and basically some range of the keys lives on whatever, maybe 1 to 40 live on shard 1, 40 to whatever 70 live on shard 2, and 70 to 100 just to make stuff up lives in shard 3. So basically you take the tables in the database or the rows in the database and shard them by key. And so when a front end needs to know, of course, which databases there are, and if it needs to get key 32, we'll go to shard 1. If it needs to get to key, let's say 50, it'll go to shard 2. And so this gives us like database parallelism. So like if most requests actually are on two different shards, basically instead of actually limited by the one machine, we're actually getting the throughput of one machine, say 100,000 times the number of machines that we have. And so that is typically the next step. Of course, this actually this step is a little bit more painful than the first step. Because now you might actually have cross-shard transactions if you need them, or if you want to avoid them, you got to sort of group the keys, that go together on the same machine. Otherwise, you need some two-phase commit type protocol if you do transactions across shards. So this step from the first, design 2 to design 3 is sort of a significant step. Now, if you grow further and further, you might think, well, you could just shard the database further and further, so fewer keys per server. But that actually increases, the sort of the risk that you actually have to do cross shard transactions. So there's another way of going, which is to observe that, like, well, maybe it's not really important that the database actually supports the reads. We can offload the reads, from the database, and basically the database only does the writes. Then maybe we can get a big performance gain. And so that's basically the sort of the next common step that websites take if they scale up is add caching. And it could be in the form of Memcached or Redis, sort of popular open source packages for caching. And then the basic plan is is sort of roughly as follows. We have a lot of front ends as before. And we have a set of caches on the site. We'll talk a little bit about that in a second, a little bit more. In the Facebook case, we got here are caches, cache layer, cache 1, cache 2, cache 3, and in the case of Facebook, these are called, each individual server is called a Memcached daemon, and the whole cluster, or the collection of caches, is called Memcached. And there's still our database, sharded across maybe multiple machines. So this is sort of the storage layer. And then sort of the idea is pretty straightforward. If a front end needs to wants to read a particular key, it first tries to cache. And hopefully, we'll hit into cache, and so basically get a quick response back, from the cache. If it's not into cache, then it can retrieve it, from the storage system, and then install, the data into cache. And writes, basically go straight, to the storage server. And this, this sort of kind of design, we'll talk about it much more in the details in a second, but this sort of kind of design where you add a caching layer works extremely well for read-heavy workloads. So if you think about Facebook, it is going to be, there's a whole lot of users, and what they're doing is reading other people's posts, looking at the timelines, maybe watching, looking at pictures, reading the news articles, et cetera, et cetera. So it's a very heavily oriented workload oriented to reads. And in this case, the reads are going to be all served from these caches, and these caches can be like dirt simple. And think about like the caching, the key value server that you built in Lab 3. The key value server itself is actually nothing more than a hash table. Maybe you want to be a little bit smart about having locks per bucket, and so that you have a bunch of concurrency within the cache server itself, or the key value server itself. But it is basically pretty straightforward. There are two challenges that come along with this. or the main challenge basically is how to keep the database and the cache consistent. That's sort of challenge one, and a lot of the paper is devoted to talking about that. And the second challenge, which is also the main theme for the paper, is how to make sure that the database doesn't get overloaded. And the issue here is that once you scale up, say, to 1 billion requests per second by using caching, if any of the caches fail, that load will shift from the front ends perhaps to the database. And of course, the database is completely not designed to support that kind of workload, and basically will fall over. And so a key challenge in the whole set of lessons that you learn from this particular paper is the techniques to basically avoid going to the database, so that there's no risk that actually you overload the database. Okay, any sort of questions so far? Let me say a little bit about consistency, because that will be, although I'm going to talk mostly about performance, it's going to be important to keep in mind, even in this sort of section about consistency, about the performance.
I had a quick question, sorry.
Yeah.
It goes back to like having the state, like the clients be stateless. So what, yeah, there we go, on the second part of website evolution. Why is it important for the clients to be stateless?
That makes the replication easy, right? The clients don't actually, you don't replicate the data, so you don't have to keep the data consistent. All the data lives in one place, mainly at the database server. Okay,
yeah. So the idea is like any client can like fail and it doesn't matter.
Yeah, it doesn't matter, and can keep going computing, and users don't have to worry about actually keeping data consistent because data is only in one place. Like a lot of the things that we've been talking about this semester, doesn't show up in this particular design. Okay. Okay, so back to sort of once you do actually cache data, you do have this consistency issue, right? And so the instant question is like, what is database? What is Facebook shooting for? And something is typical. It's called almost like eventual consistency, which is a pretty vague term. But basically, maybe to contrast it is to say it actually does not shoot for linearizability. In fact, what they're sort of shooting for is, they do want, right ordering. So rights are all applied in some consistent, total order, so that you don't get weird, going back in time problems. And that is all done basically by the database. So not really a big concern, for the Memcached layer itself. In terms of reads, it's okay if reads are behind. And that is really a property of the applications that Facebook wants to support. Again, the data that's in these caches is the data that the users actually consume. Web pages, posts, timelines, friend lists, and all that kind of stuff, or status. And none of that actually is really that important for users to see a very up-to-date picture. If it is lags behind a little bit, 1 to 2 seconds, no problem at all. Certainly, if it lags behind for hundreds of milliseconds, the user won't even notice. It's not perceptible. And so it's okay to be behind. Of course, you don't want to be behind for hours. The users might actually notice. But for a little while behind is actually not a particular big deal. So they don't really shoot, for sort of strict linearizability, where read observes the last write. If it's some reason right, that's fine. There's one exception to that, and which is that they do want to arrange that, sort of clients read their own writes. And meaning that, if one client, updates a key K and then immediately reads later that key K, it's very desirable that that client actually does observe its own write, because it actually makes it more complicated to, otherwise running applications would be even more complicated. So this is sort of roughly what they're shooting for. And this is quite a bit weaker than some of the models that we have seen before. It reminds me maybe a little bit, from about the Zookeeper sort of style of contract that it can provide. Okay, so one other thing that I want to say, go back a little bit. So we need to keep the databases and the cache consistent in some manner. And so the basic plan that Facebook follows is an invalidation plan, or a cache invalidation plan. And we'll see later in the lecture, why that is the case. But basically, what happens if a front end does a write, it goes actually to the database. Here's MySQL. But they run next to the database, another program, whatever it's called, Squeal. And basically, it looks at the transaction log. So MySQL, maintains a transaction log, to implement transactions. And, Squeal looks like this transaction log, sees, what things get modified. And basically, if there's a key that gets modified, so it sees like key K gets modified, it will send an invalidation message to the cache, basically deleting. Actually, it just issues a delete of that key K, to the appropriate cache, and that way, the data will be removed. And then at some point later, when a client comes along, does a read, it will get a miss in the cache. Read retrieves the data from, reads it from there. So here does a get. Let me call this a get. This is a read. Gets the data from the read and then actually installs it in the cache. And so one thing you might wonder, like, why actually does the application itself install the data into the cache? So it does a put. And this has to do with actually that these caches, what they're called are look-aside caches. And the reason they're sort of look-aside is that because typically what the application will do with the data that it actually reads from the database is maybe massage it a little bit. They'll do some computation on it. Maybe they'll take the text of the page and actually turn it into an HTML page or HTMLify it, and then store the result of that, the HTML version of the page actually into the cache. Or maybe, reads a bunch of different records, aggregates, some data, and, puts the aggregated result in the cache. And so the application is sort of in control in this design of what to put in the cache. It puts a little bit more burden on the front end or in the application or the client in this case. But it has the advantage, that you can sort of do some pre-processing before actually sticking something in the cache. And this sort of in contrast where the cache would be transparent, where the cache would just be sitting between the front ends and the storage server. And if you miss in the cache, then the cache retrieves the data. But of course, the cache and the database don't really know what the application exactly wants to store in the cache. And so in the look-aside design, the application is sort of in control of the cache. So in a little bit more detail, we can then look at this picture of like how actually reads and writes are implemented. So here's the reads. Oops, sorry. So this is a sort of figure 2 from the paper. And so here is our web server, that is our client. the client retrieves the key from the memcache. As we'll see in a second, typically it actually will ask for a whole bunch of keys. There's not uncommon that the web server will ask for 20 to hundreds of keys. Presumably it's trying to compute some web page. The web page aggregates data from lots of different places, and then for every piece of data that needs to be put into that web page, the client issues a GET request with perhaps with many keys. That goes to Memcache. It gets results back, and when sending that GET to the Memcache, you might contact many Memcached servers. The results come back to the web server. If anything is missing, it can process the ones that actually return the positive result, but we get nil back. Then the client goes and does a select on the database and runs an SQL query that returns some data, and the results of that, and the client might do some computation and then actually install the processed values that came back from the select into Memcache. And that's sort of the read side. And again, here you can sort of see the locus site property or aspect of this design, where Memcache is not really sitting straight between the web server and the database, but sits on the site and is managed by the client. So here's the right site. So for example, if the web server or the application needs to add a post, or put a picture in the post or whatever, the server does an update, sends basically the update to the database. This is just performed like a normal transaction. And then, of course, on the database on the site, as we saw before, we'll do invalidations using this the squeal daemon. But that squeal daemon operates asynchronously. Oops, sorry. And so the client, the write doesn't really wait until that invalidation has happened. Once the update in the transaction, once the update is done in the database, the transaction is completed, it will return to the client. And then in parallel, the squeal does the invalidations. And because the squeal does the invalidations asynchronously, the web server, just to as a precaution, does the delete of the key in the Memcache immediately. And so and the reason for that delete is only because we want to read our own writes. So when the web server, for example, looks for that key K right after it did the update, then it will miss in Memcached, and it will go and actually retrieve the new value and then install it. But that's just the case where a web server immediately reads the key K that it just actually updated a little while ago. Okay, but in principle, it's not necessary to do this delete. The invalidation at some point will happen, and will kick out that K out of the cache, and that's fine for basically other clients. But just for this client, we want to make sure that actually it reads its own rights.
I have a question.
Yeah.
So why doesn't it set after the delete?
Yeah, that's a very good question. Like, why doesn't do the update immediately, correct? And I think that's called like an update scheme, and that's in principle possible here too. But I think it's a little bit tricky for them to make work, because I think it was going to require some cooperation between the database, the cache, and the client. And I think the issue is as follows. Let's say we have a client C1, we have a client C2, and we'll see similar sort of type races showing up. Well, let's say client X1 sets X to 1 and sends that to the database. And then, so like now so this is a hypothetical update scheme. And the main point of this slide will be, or this board will be sort of talk about like doing action update is not completely trivial. Let's say client 2 at the same time, or roughly after it, sets X to 2, sends that to the database. And let's say the client 1 has got a little bit delayed. And so we're implement your scheme, correct? And we immediately do a set of K to 2. And let me say K was 0 at the end, in the beginning. So this will update Memcached D, correct? So the cache is now going to have a value of whatever K to 2. Then client 1 actually comes around to do actually its set. So it will do a set here, or put, and set put, whoops, sets K to 1. And so this will overwrite the 2, and now we have a stale value in the cache. And worse, this value sort of is there sort of persistently stale. Any get later on, we'll see actually the state value. And so this is not so desirable. And so you want to avoid that. And of course, you can make maybe the update scheme work by, for example, ordering or time stamping or assigning a sequence numbers to the updates, and then by the database, and then the key value server or the Memcached D could basically not perform updates that are out of order. But a scheme like that was going to require some participation of the database, and require modifications to MySQL. And one of their goals was to actually build everything from off-the-shelf components. And so, they prefer to go this invalidation scheme, which I think is just simpler to implement, because basically, the database, the only thing it has to do is this like additional process that sits on the side and uses the standard delete operation that Memcached D already supports.
Thank you.
Does that make sense? And we'll see a similar issue like this one show up later again, correct? And, because there's you remember from the paper, there's some discussion about these tokens or leases to deal with stale values. But that's going to be, as we'll see, stale values on the read side, or stale values that sort of have an interesting interaction between readers and writers, but can be solved totally in the context of Memcached D without actually making any database modifications.
So why do we have a separate process to basically issue the invalidation? So this Siegel, I think it was called.
Yep.
So why? So like, why do we have this process if the front end itself will issue a delete K anyway?
We'll see later on why this is going to be very useful. Okay. And particularly, what we're going to do is we'll see is that the cache is going to be replicated, and we need to set an invalidation to every replica. Okay, I see. Thank you. That's
it's not going to send a delete to every Memcached replica.
The Squeal, yeah. We'll see in a second. Hold on, and we'll see that in a second. In fact, I was going to go talk about it right now. So far, actually, most of this story is pretty standard. Small changes here, and what we talked about so far is really, nothing really too exceptional. Things get more interesting right after this, and so we get more into sort of Facebook-specific optimizations or performance tricks. And the first thing that we're going to see, so let me get this in order. Okay, so I need to go back. The first thing that actually that sort of becomes unusual is that actually Facebook basically replicates a complete data center. At the time of the writing of this paper, there were basically 2 data centers. One on the West Coast. Let me switch back to blue. So data center 1, they're called regions. Here's data center 2. And they basically have, they're all have a client layer. I'm just going to, so a lot of front ends. And maybe this is the one on the West Coast. And then, there's the Memcached or the Memcached layer. And both have their own Memcached layer. So here's this set of front ends again, a lot of front ends. So here's a lot of Memcached, a lot of Memcached, a lot of Memcached here. And then, there's the storage layer, which is our, sort of sharded, databases. So a lot of machines here too. And basically, the data center 2, the one on the East Coast, is a direct replica of the one on the West Coast. And the scheme that they use for writes, because now we have 2 replicas really of the data, correct? The data of the database is stored in 2 places. So we need to keep in some way, these 2 copies up to date. And the basic plan, at least on the right side, is to all the writes are going through the primary. And one of the regions is the primary, the other is the backup region. So this is region 2. And in fact, I think in the paper, the West Coast is the primary. And the East Coast is the backup. And so all writes actually go through the storage layer on the primary. So even writes issued by the front ends on the East Coast go to the database here. And so the database there on the primary just runs the transaction. And we know, and then basically propagates these invalidation messages, or well, first of all, it takes the log that actually sits on this site and basically copies it or transmits it over to the other site. And so this is the squeal process that basically does that. And that process basically applies the log to the storage the database on the other side. So keeping the 2 databases in sync. And as a side effect, it might actually send invalidation messages or delete messages to delete keys. And so you might wonder, why do it in this way? Why not keep, for example, everything on the West Coast and, basically double the number of, memcaches and all that kind of stuff. But, the one primary reason to do this is this gives good read performance for users. Good read performance for users that are actually sitting on the East Coast. So, they will connect, to one of these guys. They will look up the data in the cache, their Memcache on the East Coast, and basically return the data straight out of the Memcache. So we're basically going to get really good, one, we can still get our good read performance. In fact, we can also get low latency because we're basically, reading from a replica that is close by. Of course, these caches, might get a little bit more out of sync than the example there in the single data center, because this whole updates and invalidation, all happens asynchronously. But that's more or less, a little bit okay, correct? Because we already said that we're actually not looking for, strict consistency or serializability.
I have a question. So, if someone in the East Coast, if a client in the East Coast writes directly to the storage on West, right?
Yeah.
Which it doesn't invalidate.
This guy also will send invalidates to its cache.
Oh, but we said right. But we said the client itself to read its own rights. Its own rights.
Yeah. So where does this go? That of course goes through here, correct?
Yeah. That makes sense. Okay. Okay.
Okay.
I've got a question too. Do clients always talk? So will a given client always talk to the same Memcache server?
No, because going back a little bit earlier, and we'll talk about this in a second because this actually is a problem, as we'll see. So if a front end basically talks, the keys are sharded across the Memcache servers, correct? And so whatever key K1 lives in C1, K2 lives in C2, et cetera, et cetera. And typically a front end, when it needs to construct a web page, it needs to get a whole bunch of keys. And so it sends actually these requests basically parallel to the different Memcached Ds and gets all the responses back. And so in fact, the front ends are very likely to talk to every Memcached D in the system.
I see. But for a given key, it would always talk to the same server.
Yes. Yeah, they actually happen to use consistent hashing. So if we'll talk a little bit about a second, a little bit more, but like if the one Memcached D serves goes down, correct, can't talk to that one anymore. And so it might be over time that the assignment from shards to servers will change a little bit.
Sorry, actually, just a follow up on that. So the requirement for clients to read their own writes is kind of like a weak guarantee, right? Because if the server that it deletes from goes down, and then it has to read from a different replica, it might end up not reading its write, if in the presence of a failure.
Hold that thought for a little while, okay? Then we'll see there's a number of couches or races, if you will, and they have different techniques for solving those races.
Sorry, final question.
Yeah. Final. I like.
So we're doing read for read our own writes. We make sure that we go directly to the storage servers right after a write, correct?
Yes.
Validating the cache. But you also said the
No, hold on. When you do a write, you do the update in the database.
Right.
And then you delete the K from your system. So, for example, in this particular case, you would do a write, to the primary, delete the K from your local cache.
Yep.
So when the next time you do a get, you're gonna read from the storage server again.
Right. Exactly. Yeah. But I was curious. So you also said the write to storage happened asynchronously, right?
The replication happens asynchronously, and the invalidations happen asynchronously, not the writes.
Okay, the writes are synchronous.
So you do the delete after you finish the write.
Okay, great. Thanks.
Okay.
I have a question here. So if you do a write and you're from the so you're not from the primary region,
Mm-hmm.
and you do a write to the primary storage, and then you invalidate your memcache and then do a read, but you do a read from your storage, and maybe your storage isn't up to date yet.
Yes. So you got a race, and so we'll see how they solve that.
Okay.
That's correct. But first, let's talk more about performance, because this is not good enough for them yet. They want more performance. And so, if you're sort of broadly speaking, there's sort of two strategies for getting performance. And just stepping back a little bit. And we already seen them a little bit in a very high level. So there are two basically plans. One is to partition or shard. And that's very cool, because in fact we see that it's being used basically both on the storage layer and the memcache layer. And so if you need more capacity, you just buy another server, change the hashing function, and suddenly you got more capacity in your Memcached D, and you can hold more data, right? And that data can be accessed in parallel. So you get a lot of capacity. Plus in the capacity, plus in the parallelism side. But if you have a particular key that's extremely hot, like a lot of clients actually need to get that key, whatever, a particular person on Facebook who has a timeline that everybody's following, then that key is going to hit a lot. And it's being served, luckily in this case, it's being served maybe by two different servers, one in the West Coast and one in the East Coast. But presumably a lot of clients on the East Coast and in the West Coast, we're going to hit the same, or the Memcached D server on the West Coast and the Memcached D server on the East Coast that hold that key. And so that's not going to be that good, right? Because that single server might actually get overloaded. And it turns out the key distribution varies widely. And so that's not so good. And so to solve problems like that, the second sort of approach is to replicate data. So here's partition data, and now there's replicate data. And that's great, for hotkeys. You can take the same key, replicate it on a bunch of different Memcached servers. Then the clients that all meet that key can be spread across, those Memcached servers and get the keys basically in parallel. And so that works actually good for hotkeys. It doesn't really increase your capacity, right? So you just takes more. And in some ways, we can see that in the previous picture, we have replication in action here, correct? We have replicated one data center, from the West Coast completely to the East Coast. That hasn't increased the total capacity for the Memcached because both the Memcached layers, store, store the same amount of data. Didn't increase the capacity of the Memcached layer. But you're allowed to now read from these two different Memcached layers on the East and the West Coast in parallel. Okay, so we see a little bit of form of replication going on, and you might wonder, what else is left to be done? And this comes to the question that was asked a little bit earlier. Let's say you need more capacity now, right? So, well, when one solution to more capacity, even in a single data center. So forget that there's two data centers. Just think from the perspective of a single data center. We want more capacity. Well, one option, correct, would be to just buy more Memcached servers and just keep buying more of them. And that turns out to be slightly problematic. And one reason that is problematic is because these front ends talk to basically every Memcache server. And so they, almost at least for writes, we know that they have TCP connections open, and so there's a large number of TCP connections. And furthermore, as we said before, if there actually is a particular key hit hard, then that doesn't really solved by sharding. So you can buy more machines, but if that one key is hot and lives in one machine, that actually is not going to really improve your performance. So the next step in terms of performance improvement is to actually replicate inside a single data center. So more performance. And this is this idea of clusters. And this is really a story about replication. And so what they actually do is, if we look in a single data center, we got our storage layer. And then within the storage layer, basically we're going to replicate a set of front ends. So here's our front end layer, and here's our Memcache layer. And we're going to take that and just replicate it multiple times. And then they call this a cluster. And the reason this is good, is this actually does deal well with, it's good for popular keys. A popular key will now be replicated, potentially in multiple clusters. And so that is nice. Second, it reduces the number of connections. And this is actually particularly, there's multiple reasons why this is important. It avoids what they call the incast problem, incast congestion. And so, as I said before, one of these front ends may have to retrieve, 500, whatever, 100, tens to hundreds of keys. And so it will send them in parallel to all the particular Memcaches that are important, and they will all respond. And of course, we have many more Memcaches. We're going to have much more parallelism. A lot of packets will come back exactly at the same time. They can easily lead into queues being overloaded or queues being full, and therefore packets getting dropped. And so by reducing the number of connections that actually every front end talks to, reduces the number of responses that are going to come back, and we avoid this in-cache congestion problem. And in general, it sort of reduces the pressure on the network. It's actually hard to build networks that have a bisection bandwidth that can sustain a huge load. And here, by sort of using replication, basically the network, for one cluster really has to support that one cluster well. Now, so this is all good. Of course, this is the downside of a design like this is that if you have unpopular keys, there's unpopular keys going to get stored in multiple regions and basically, do nothing, or don't really contribute to improvement in performance. And so, in fact, what they do is they have one additional sort of pool that they have, and they call this the regional pool. And applications can decide to store not so popular keys into the regional pool. And to just stick it at the side, and so that these so that they don't are replicated n times across all clusters. So you can think about a regional pool being shared among multiple clusters and used for the less popular keys or less infrequently used keys. Okay.
Sorry, so this is going to help with popular keys because each cluster is going to have its own memcache.
Yep. Yeah. Every cluster has its own memcache. It has its own front ends. It has its own memcache. And basically, users, the users are basically load balance across all these clusters.
But this still does not increase capacity, right?
Does not increase capacity. If you want to increase capacity, well, it increases capacity a little bit, correct? Because like all the unpopular stuff is not being actually cached and is stuck in the regional pool.
Okay.
And so that space is now free to actually store other keys.
Mm-hmm.
So to avoid in-cache congestion, they would also reduce the number of shards per cluster, right?
Yeah, or don't grow it. The alternative plan, correct, was not to introduce clusters, but basically keep growing the memcaches, shards, the number of shards in a single memcache. And that has its own limitations.
Makes sense. Thank you.
Okay. Well, so this is sort of the base design, except there are sort of all kinds of performance challenges that they had to resolve. And most of these performance challenges really have to do with, I think the way to think about it is protecting the database. So like, just to go back to this picture, correct? Like we have now a design that apparently can support billions requests per second, but the storage layer itself, is sharded, but can certainly not, sustain billions requests per second. And it would be a disaster if, for example, let's say all the memcaches failed or some way or another, or a whole cluster failed, and all the front ends, would hit the storage servers. Then the storage servers would fail over. They couldn't handle that kind of load, and so they got to be very, very careful with actually doing anything that requires more load than the storage servers. So one, for example, challenge, I'm going to talk about a number of them, is to bring up a new cluster. The easy way to bring up a new cluster would be just to, build the cluster, turn the machines on, install the software, and be done. And basically rely on the fact that, if the data is not in the cache, you will have a miss, and then we'll go to the database and actually, collect the necessary data. And what is the problem with that kind of design?
It's going to have a lot of cache misses because there's nothing in the cache.
Yeah. For example, let's say you had one cluster and you added a second cluster, right? And you moved half of your users to the second cluster, right? Then 50% of sort of your requests are going to miss in the cache, and they're going to hit the database, and the database will fall over, right? So how do they deal with this?
Gutter.
No, not the gutter. This is the.
I think they were making the new cluster read some entries from the cache of an old cluster.
Yeah, correct. So gets in the new cluster. If they miss in the new cluster, they go to the old cluster from an existing one. And then they set in the new cluster. So basically, one way to think about it is they fill up a new cluster or warm up a new cluster by reading from an existing cluster. And so that maybe increase the load on an existing cluster a little bit, but at least it won't actually put a lot of pressure on the database. And as we'll see in a second, that also introduces again some consistency issues, and we'll see that a little bit later. Okay, so that's one example of a performance challenge that they addressed. The other performance is a popular term used in many contexts that are called the thundering herd problem. What is the thundering herd problem?
I guess when there are a lot of writes and reads approximately at the same time, and because there are a lot of writes, the data will be invalidated many times, and the database will be assaulted with requests.
Yeah, and you can make it even simpler. Like a single write causes an invalidation of a key, correct? And anybody, any client that reads the key right after it. So like you could have the following situation: you have a very, very popular key. You invalidate the key, so you delete the key from your cache. All the machines or all the front ends that need that popular key, will do a get on that key, all get back nil, and then they all want to like read select from the database, correct? And that might cause it puts a lot of pressure on the database. So they want to avoid that problem. And so how do they do that? How do they avoid that problem?
They use leases.
Yeah, exactly. Go ahead. Say more.
Oh yeah, yeah. I think like they gave like a time like for key specific for the user, and then like some time. What I understood, it was like kind of a lock, and then like if another user tries to like use it, they will like wait, and then hopefully it would be updated fast enough so that in the next retry they will get it.
Yeah. So basically, okay, so the get, if you do get and you get nil back, you get two situations. Either you got a lease, right? The first client basically that does a get and misses, gets a lease from Memcached, and that Memcached, that lease basically gives it the right to do an update, or tells the client like, you're responsible for doing the update. And if you don't, the first one, then you get basically a retry message or result, and that basically tells the client like, oh, you should retry it soon and not immediately, and maybe spread around a little bit. They probably do some binary backup type style thing and retry the get. And most cases, the client that the first client that missed will have updated the key K reasonably soon, like in the order of milliseconds, and then these retries actually will succeed. Right, and there's no explosion on the number of requests to the database with this scheme. Of course, it introduces, as we'll see in a second, more race conditions. But first, let's keep focusing on performance.
There was another thing about leases, right? Where they addressed stale sets.
Yeah. So leases form two roles. As we'll see in a second, one for consistency and one for performance. This one is for performance. And so we'll talk about consistency in a second, and then we'll see the second use. as one way to solve one of these race conditions. Okay, one more. There are many more in the paper, but just one more that's sort of interesting, at least I find interesting. What happens if they have a Memcached D or Memcached server failure?
It depends if it's the whole data center that, well, the whole collection of Memcache servers that failed. Or if it's just a
Just
few.
consider a handful.
I've
one or
just
two.
used Gutter that someone mentioned before
Yeah,
to set the Memcache, the failed Memcache, but they don't delete them.
yeah. So the scenario, correct? The problematic scenario is like a Memcached D server fails. That will result in a bunch of misses. Those misses will hit the database, and they want to avoid hitting the database, correct? Any client that actually has a couple keys at those servers is going to try to retrieve the key, will fail, and then has to do something. So when a get fails, the easy solution is to go to the database, but that, we want to protect the database, and so that doesn't seem to be a great idea. And so what they do is actually have a small other cluster or another pool, like the regional pool, they're called the Gutter pool. And the Gutter pool is basically sort of a handful of Memcached D machines that is just available. And they're available for sort of the short period of time that the system sort of reconfigures and repairs itself and adds new Memcached D servers to replace the ones that failed. But in that period of time, that's in the order of minutes or maybe a little bit more. They don't want the get request or the selects to go to the database. Instead, what they do when the get fails, you go try first the Gutter pool, and the Gutter pool will, the first one that hits the Gutter pool, will fail or will miss. Do a select in the database, get the result, stick it into the Gutter pool, and then subsequent requests or gets will actually then be answered from the Gutter pool. And at some point, the Memcached D machine that was failed, has either been replaced or replaced with another machine or recovered. And then, the load just shifts back to this Memcached D server, and the Gutter pool sort of sits again in the site to sort of carry over between these sort of transition periods. Okay. And so this sort of gets us to the reading question for today. As you just mentioned, the Gutter pools, you don't do a delete from the Gutter pool. Invalidations are actually also not sent to the Gutter pool. The question is like, why, or can we speculate on why? And so maybe this is a good time for a quick breakout room, a couple minutes, to either discuss other aspects from the Memcached D design that you want to discuss, or try to figure out what the answer to that question is. So maybe we can do a breakout. Yes, thank you, Lily. Okay, is everybody back?
Yep, looks like it.
Yep. Okay, good. Okay, so anybody, of course, the paper doesn't answer this question very precisely, but anybody who wants to dare to speculate what the answer is on the deletes, no deletes to or no invalidations to the gutter cluster?
We
What
said
said-
that.
oh, sorry.
Yeah, go ahead.
Oh, what we said was something like, if you do, then it would have a lot of pressure on the gutter pool because there are so few machines. And for every cache miss, there are 2 requests, and for a cache hit, there's just 1. So if you do that after every write, you would have an extra request on the gutter pool, and it's so small, so you don't want to do that. And also you would protect the database as well, because you would constantly query it after a write request.
Yeah, exactly. I think, and in general, the delete messages also will have to go to 2 pools, correct? The original Memcached pool, all the Memcached pools that need to be invalidated, and to the gutter. And so, you also double the delete traffic. So I think that's I think that's the reason. It's a small set of machines. It's just there to sort of basically get you through that transformation from a deleted Memcached server or failed Memcached server to a new Memcached server. Good. Okay. So that's all I want to say about performance, even though there's more in the paper about performance. Instead, I want to talk a little bit about sort of these races that sort of come about because of this trying to achieve the high performance that we've been talking about. There are going to be 3 races I want to talk about. And in fact, I think all 3 you already identified. And so basically, most of the discussion is presumably going to be about how they avoid them. And so race 1 is what they call stale sets, and the scenarios swallows. We have a client 1, and just one region, nothing, or one cluster, nothing particularly special setup. So the client 1 does a get of a k. That turns out to get a nil in the scenario. It will read the value from the database. Maybe this is the client that actually got the token, correct? And it's the one that actually is allowed to set it. But before it actually gets to the set, another client comes in and writes k is 2 to the database, and then does a put of k on 2. And then the other client actually finally gets around to doing actually its put. So it does a put of k comma, and this is like maybe v1. So k comma v1. And now we have a stale value in the cache, and that stale value is sort of permanent there until somebody else does an update. Okay, and that's sort of undesirable, right? That really breaks their sort of contract with the applications. They don't want to go back in time. Would be anomalies that actually the user could observe, and that's what I want to sort of try to avoid that. And so, how do they solve this problem?
With leases?
Yeah, correct. And some say the leases help out here. They already have a lease, correct? Because this guy got a lease must have gotten a lease because otherwise he's not reading from the database. And so at the client 1 presents this lease at the put, or can present the release at the put, and in fact it will. And what is the additional step basically?
To check that the lease hasn't expired or something, because if the other client was able to.
Oh yeah, sorry, I just realized I made a mistake. So this is why the question is also not so good. Let me see. The client 2 doesn't do a put, correct? That was an invalidation consistency. I got myself confused here. So what does the client 2 do after it sets the database? going back to
Delete.
Yeah, it does a delete for the reason that we talked about earlier, correct? So it does a delete of K. And what's the side effect of what happens with the release of a key that's being deleted?
It doesn't like verify, or it doesn't.
Yeah, actually, what happens at the side as a side effect of the delete, the lease is invalidated. So it invalidates the lease. And so when the put comes along, so my timeline is a little bit, this happens like well before, right? So the put happens after the delete. The put will present the lease that it got at the get, but that lease has been invalidated by the delete, and so this put gets rejected. So basically, one way to think about this is that they leverage, the lease mechanism to avoid the funding hurt problem. They extend it to basically also avoid this stale set problem. Right? Does that make sense?
Like from my observation here is that even if we don't have this lease invalidation mechanism, we would still obey the weak consistency that you would have ordered rights that happened at some point in the past. But I believe that the thing that this thing ensures is that you observe your own rights, right? Because
you observe your own rights. That also ensures that you don't go back in time, right? Like if you read something and like everybody else that comes now after this client 2 will see, the old V1. And so a client might get well behind and not see that new right for a long, long period of time. In fact, one might see not at all.
Yeah, but I mean, would this be actually going back in time because clients did not read anything after V1?
Maybe back in time is the wrong word, but it won't observe V2 for a long, long time.
I see. Okay.
Right, and that was not something that we wanted to happen.
Mm-hmm.
It's okay behind a little bit, but not, for a long, long time. Okay, second race, which you guys already mentioned, identified too, because advantage of many, I guess, lab debugging, know all about races. Race 2, and this is the cold cluster race. And sort of in a similar style, we have 2 clients, client 1, we have client 2, and let's say K is V1 originally, and so both clients are in the cold cluster. Client 1 sets the key to a new value in the database, deletes the K in the cold cluster, right, in the current cluster that's actually in. And then this client does a get in the cold cluster, sees that it actually is not there, and it is going to do a get from the warm cluster, get the value back. Maybe that get actually gets there before actually the cold cluster or the warm cluster actually has been updated. And so now it will do a set of, the K to V1 or put, sorry, let me be consistent, put of K to V1 in the cold cluster. And now we have sort of the same situation as before, where we have sort of a permanent stale value in the cold cluster. And how do they solve that problem? Anybody remember? So they have a small extension that avoids this problem. Any guesses what it could be if you?
Wait, so C1 in the warm cluster or cold cluster?
No, both in the cold clusters.
Oh, and they're in different cold clusters, right?
I'm not sure that matters.
Yeah, actually it doesn't.
Anybody?
I think they mentioned like a hold off for 2 seconds, though
Yeah.
I'm not entirely sure about all the details of that.
Yeah, basically this actually causes, they put a hold, they call this a hold off, a 2-second hold off on any sets to that key. So this particular, after you do a delete in the cold cluster, you can't do any sets to that key for 2 seconds. And so this particular put will be rejected. And this is only during the warm-up phase, correct? So when the cluster comes up, it's cold, for a couple hours it runs, to sort of start warming up and get its content in place. And once warmed up, then they stop doing this trick. But basically, sort of to this paste this problem over, they think that 2 seconds is sufficient, and that's sufficient for basically that write to propagate to the cold database too. Okay. Good. There's one more write problem. Let me quickly mention that because again, you already mentioned it. So race number 3 that they talked about in the paper, and I'm sure there are more, but the one they say the one that I talked in the paper about, and this is between regions, and it has to do with the primary and the backup problem, primary and backup. And it's sort of a similar problem, and where the client 1 does a write to the database, and this is a client in the backup. So this is a backup client, sits in the backup region, so it does a write to the database in the primary region. So it goes off, and then it does delete of the K in, of course, the backup region from its cache. And then in principle, it would do immediately, and this is like one of you mentioned this, like if you immediately do a get of that particular K, right? Then it won't see the, it will fetch from the, it won't see actually the result of that write. So it won't see its own write because that write is still on the way to the backup or to the primary. The primary will send through the SQL thing, squeal thing, and propagate the update to the database in the backup area. And so only then, a get in the backup will actually, in the backup area, in the backup region, we'll actually see the K change. And so we have a problem here, correct, where if this K would proceed as so without any modifications, then we would see not our own writes. And anybody remember how they solved this problem?
Was this the remote marker?
Yeah, absolutely, it is. So when they delete this K key, they keep it in the Memcached of the backup and mark it as remote. And so when this the client 1 does a get, it will see, hey, I'm going to get basically gets remote back from its local Memcache, and then it knows basically to fetch it from the primary. from primary region. Okay.
But then the remote marker will be removed when it's safe to read from the backup.
Yes, I think when the database, the backup database gets the data from the primary, it can remove the marker. Because then it's safe to read it from the primary database, or from the backup database. Does that make sense? Okay, so let me do a quick summary. And because I'm running a little bit over time. So quick summaries, caching is vital. To basically get this kind of capacity that we're talking about, this paper, like billions of operations per second. There's sort of two strategies to sort of get this high capacity. One is partitioning, which gives you sort of parallelism or sharding. And the other strategy is replication, which is really good for hotkeys, keys that are being requested by lots and lots of clients, so that actually the keys get replicated on multiple machines. And we also see that there's sort of a bunch of almost ad hoc techniques to sort of get around some of the serious consistency issues that pop up, even if the system is only designed to give weak consistency. And so this whole sort of consistency between the database, between DB and caches or Memcached is tricky, maybe much more tricky than you might have thought, because Memcached is just a cache. What could be the problem? But then, as you can see, it's actually pretty tricky. And in fact, there's quite a bit of research going on trying to figure out how could you do better. Okay, with that, I want to conclude so that people that need to run can run or go to their next Zoom meeting. And but I'll stay around and answer any questions if you have any questions remaining. And otherwise, I'll see you first thing. Thank you.
Sorry, I have a question about, so for example, for the last thing we talked about with the remote marker, how did they know that this is going to be a relevant data race? Or how did they decide that it is going to be more useful to do this additional steps of remote marker versus just getting stale data?
Well, I think that is because they had this requirement right up front, although the paper didn't really stipulate it very clearly. They really want this. Like, for example, you do a user adds something to their timeline, read it again, and it's not there. And so that is a thing that could just be observed directly by users, and a strange inconsistency, and they want to avoid that.
Okay, that makes sense. That makes sense. And my other question was on one of the first slides where you had invalidation of the Memcached.
Let me find where I had that. Right here. Well, yeah, this is the invalidation slide. A little bit wild now, but.
Oh, no, it was one of the later ones.
Well, this also has invalidation on it. Oh, no, it isn't.
Maybe the next one?
Yes, here we go.
Oh, yeah, that one. Yeah. So the client is going to set the invalidation only for its local region, and the squeal is going to do it for the transfer and for the non-local.
Yeah.
Okay, that makes sense. Okay, thank you so much.
You're welcome.
Professor, I had two.
I thought you had your final question. Sorry. It was a no, go ahead, please. Ask more questions.
These are after class.
They don't count.
So first, so servers in a region are assigned when we have clusters. Each one are assigned to a cluster, right?
Yeah.
Okay.
So every cluster is really a replica.
Okay, nice. Yeah, and like servers are assigned to one single replica.
Yeah,
And
yeah, exactly.
Nice. And then the second one was like straight from the paper and very precise, but it says like, okay, here in, I think, generic cache in page 2, it says like the use Memcached as a more like, general key value store. And in particular, they say it takes little effort for new services to leverage the existing Marcher infrastructure without the burden of tuning, optimizing, provisioning, and maintaining a large server fleet. So I wasn't sure, and I looked up and I couldn't find what's existing Marcher infrastructure.
I don't actually know exactly what they're referring to. So
Okay, all right, cool, thanks.
Yeah.
All right. Nice. Good day.
see you.
I wanted to follow up on a question that I think William asked about a certain failure mode if
Yeah.
a Memcached server fails. I think there was a I'm trying to think which slide would be helpful to look at. I think it was earlier. Oh, maybe that one, the one you were just anything that kind of shows the Memcached, the overall system diagram, I guess.
Okay, well, there are multiple those. But this is the one basically, if you think about it as a single cluster, if you will.
Yeah. Okay.
And
yeah,
we could look at another one, but I think this is sort of probably good enough then.
Yeah, I think this is good. Yeah, I think his question was so shoot. Trying to remember it. But it was something about like if a front end writes if a client writes to its Memcached server, and that Memcached server crashes, and then the client immediately then it presumably switches to another Memcached server and then reads it again. What mechanism makes sure it doesn't see that it sees the result of its previous write?
I think what happens is it would probably go to the gutter. Because when the Memcached fails, correct, that client will get a no response back. And when that no response comes back, it actually goes to the gutter, which has nothing in it, probably in the first try, and we'll read it from whatever database.
Okay, that makes sense.
And yeah, it's a little bit unclear exactly what happens when a new machine gets added. They don't really talk much about it in the paper. But I presume this is actually the consistent hashing part where keys will sort of be automatically shifted from one machine to another.
I guess if there were multiple clusters, wouldn't it not? Maybe I just need to reread about the gutter, but wouldn't it potentially shift to another Memcached in the? Oh, actually, it wouldn't.
No. I think always when a get fails, the client goes to the gutter.
Right. Okay, yeah, because clusters are kind of self-contained with the front end and the Memcached.
Yep.
Okay, that makes perfect sense. All right, thank you.
You're welcome.
To follow up on that, when it falls back to the gutter, what if like two different clusters, their Memcached server fails like at the same time, and so they both go to the gutter, and now we're doing like concurrent writes to the gutter. How do we ensure that those writes don't go out of order?
They do sets, correct? And the writes always go to the database, to the primary, and the primary orders all of them. So I think writes are always ordered. The only thing that the clients might do is set a value in or put a value into the KV server. But then they have done that after they've read from the database.
Right. So what if someone's like they do a read, and then they're setting it into the database, but like, let's say two different clusters fail. And then I'm not sure if this is possible actually, but let's say like cluster one first reads from a key, gets back the value, and then there's a write in between. And then the second cluster then reads, and then they both try to put into the Memcached servers, but but let's say those servers fail.
Yeah, maybe. So it's a good question. I think there's all kinds of little corner cases that are actually not described the case. I think maybe leases will help out because that server you're going to set to doesn't have the lease for the first client who did the get got a lease back, correct, to do the set. If in the meantime the service gets replaced, the replacement server does not know that actually the lease was granted, and so we'll reject the set. I'm just speculating, correct? But
Okay, yeah. So for the gutter, how does it control leases there?
I don't know.
Oh, okay, I see.
Sorry, I can speculate, but certainly I don't know.
What would you say if you had to speculate?
Well, I would first have to go sit down and think a little bit about it.
Okay, that makes sense. Yeah, thank you.
I have a bit of a tangential question, which is, I thought it was really cool that they were using UDP for the GET requests and then TCP for the others. And I was wondering like how common that is. Is that like a very standard thing to do?
Yes and no. It is, people prefer in general to use TCP because it provides reliability, ordering, and all the great stuff. But there's real overheads with it. Like the state that needs to be maintained per connection. And so there's always a little bit of a struggle. Like when machines have a lot of incoming TCP connection or a lot of outgoing connections, that always causes problems. And the default, if you run into that problem, is to basically do UDP type stuff. And
so this isn't like novel from this paper.
No, it's not novel from this paper. And some people actually roll their own sort of like reliability transport protocol over UDP.
Like Quick?
Yeah, for example.
Yeah, because they mentioned they also do like sequence numbers for the
exactly.
UDP connections.
Yeah.
Okay.
But presumably they don't maintain congestion windows and all the other scaling and all the other TCP features that TCP has.
Okay. Thank you.
You're welcome.
I have another, oops, sorry. Go ahead.
Okay, I guess I just wanted to quickly ask about kind of the replication between the different clusters.
Mm-hmm.
But basically, they don't do any formal replication, right?
Yeah, correctly. There's well, yes and no, right? Because the databases need to be updated. Oh, hold on. Well, let me actually go back and see, make sure I know what you're talking about. Let's see, clusters. Yeah, we got multiple clusters. Yeah, there's no real replication going on between the clusters, right? Because there's one single storage layer.
Right, and so they're kind of like depending on these leases to keep the caches up to date, or
every cluster is completely independent, right? They have nothing to do with each other, and users are divided over these clusters. And so one user talks to one cluster, and then within the cluster, they use leases, and the database invalidates leases and keys.
Right, got it. Okay, yeah. So it's like the squeal and the storage that kind of manages all of the consistency.
Yeah, all the writes basically in the end just go through the storage server, correct? All writes go through here. They get ordered, and they pop out as invalidation messages.
Got it. Thank you.
Yeah, go ahead, Brandon.
Yeah. So tangential question. And I guess I'm not sure if this is because of the way we've kind of presented papers in the class, but it kind of seems like the way these systems are developed is like, okay, we have like these systems, like our needs are continuing to scale. So let's like, maybe this is also not an accurate representation, but it sounds like let's add another layer to kind of handle this load, or to kind of, cache something, or add like another layer of complexity on top of it. Is it fair to say that like system development has generally been like, let's just add another layer to kind of deal with
No, yes and no. I think the designer of the system took a very pragmatic approach, to figure out like, run into a real problem and solve the real problem. And basically, if you think about it, not a lot of additional mechanism, right, to actually make it all work. So in terms of, I mean, I think it's pretty impressive that you can get this kind of performance and they have off-the-shelf components.
Right.
Absolutely, people also go back once in a while and say like, okay, how would I design a system to get better performance and don't, for example, have these inconsistencies between the database and the caches? It actually turns out to be a research problem, because people haven't really figured out how to do that. And so you'll see recent research papers that describe alternative solutions or new components of a solution, because any of the proposals I know of, cannot support 1 billion operations per second.
Yeah, right. Okay, that's interesting. Thank you.
Yeah, this is fascinating stuff. It's like a real world system design.
I have one more question, if you don't mind.
Yeah, go ahead. No.
So in the design here, where they replicate across different regions. So sorry, just to clarify, the first clarification question I have is when they replicate against different regions, each region has like a bunch of internal clusters, right?
Yes.
And then my follow-up question to that is, it seems like everything's hitting the primary storage. If let's say we wanted to scale up so that we didn't have all the writes hitting the primary storage, how would you like go about designing that work?
Yeah, my suspicion is that actually the design that's correct. Okay, so there's a bunch of points of that. There's a whole other paper on this topic about actually how to do the replication. So this is not the only Facebook paper on scaling things up. There's a system that was published in 2015, or Wormhole, where they have a sort of scalable design to propagate these writes. My suspicion is also that they will or have shard the users to particular regions and make some regions the primary for those users.
I see. So they assign different regions primaries for different shards.
Yeah, I think so. That's what I would do or try to do. And I'm speculating here. But
would it be a wise decision to do like a consensus protocol across the storage layers, or would that just be like too high maintenance?
You could do that. Like Spanner does that, correct?
Right.
And how fast is Spanner?
Pretty fast.
Maybe look back into the table. How many transactions per second could it do?
I do not remember the exact number.
I think about 100. Effect for I think wide area 10.
Right. This is for write transactions, right?
Yeah.
Okay, right. The write transactions are very slow.
Yeah.
Sorry. I think I realized that I did not understand race 1.
Okay. Let me see if I can replicate it.
Oh. Yeah.
Let's see where we race 1.
I think I'm just confused. What is V2?
V2 is this right. Hold on, I'll mark it.
Okay. And the problem is that it is like wedged in between the first one.
Yep.
Okay. Okay. So like we wanted it to be deleted so that the next person can refetch it from the database, but now it's there with the old value.
Yeah, so basically we have a permanent stale value. Really the issue is this permanent business. Or permanent between quotes, correct? Because it's a cache. But like no, this put that came after basically the K being updated to V2. So we have K2 here really, correct? That's what the right value should be. And here this is V1. So let's say this is 1. And what we've done here is we actually put a K1 in after and that's just not the right thing.
Okay,
And
okay.
everybody that comes after now and does a get on K, correct, is going to get 1 back instead of 2,
Okay, that makes sense. Okay, that makes
including
sense.
client 2, which is going to be bizarre.
Right, right. Okay, that makes sense. Thank you so much.
You're welcome.
The part in the beginning about the evolution was also pretty helpful, I think.
Okay, good.
Thank you so much.
You're welcome.